Mendeleev was given credit for the very first periodic table. Second most packet. Let's go. All right. However, quick little note, yes, Meyer was also coming to the same conclusion, didn't publish in time, didn't get his stuff out, so he didn't get the credit, of course. But it is acknowledged that he also came to some of these same conclusions as Mendeleev did as well. So, Mendeleev, moving on. Mendeleev was actually quite ingenious because he left spaces open. He did it by atomic mass, which we now reordered it to being out of atomic number. Moseley did that in like 1912 or something, back in World War I time, which is makes more sense because the identifying particle that identifies the element is the proton. So putting it by proton number is actually probably a better idea. There are a few masses that are out of order anyways. Okay, but he was very ingenious because he left spaces open and could predict properties, realized that certain chemicals behaved the same way, and basically behaved a lot of the same way due to their valence electron. That's their chemical reactivity property. Okay, because valence electrons do the bonding, so the behavior of those valence electrons are similar in the groups. Okay. Now, effective nuclear charge. You don't know this one. You do need to write it down. Effective nuclear charge is the word you're going to use a lot when you're describing and justifying your trends. Okay? Effective nuclear charge. Now, it takes into account two things. Two things that you need to know. We're talking about electrons are both attracted to the nucleus and repelled by other electrons. Attraction to the nucleus because the nucleus is comprised of protons. Protons are positive. Protons attract negative things. That's a Coulomb attraction. It's an electrostatic attraction. So, protons, electrons attracting to each other is going to be the force pulling them close. But because electrons repel other electrons, you have a factor of some electron repulsions going on, wanting to push them out. So the more electrons you have, more repulsions, you have less effective nuclear charge. Effective nuclear charge is calculated using a formula. ZF, effective nuclear charge, is Z minus S. The Z value is the atomic number, or basically the proton number. Proton number is the atomic number, so Z is going to be that particular deal. Now, the S is the screening constant, which takes into account the electron repulsions. So that S, screening constant, it's taking into account the electrons that are doing some of the repelling. Okay? So, if you have more protons and less electrons, you're going to have a higher effective nuclear charge. If you have a lot of protons, but you also have a lot of core electrons, those core electrons are going to subtract out some of that, pull from the nucleus, so you're going to have a little bit less effective nuclear charge. Okay? So, trends, starting with ionization energy. Ionization energy is the energy needed to remove an electron. Remove. What do you need to break that electron off? Remember, you can break off electrons, okay? You can add in electrons. Breaking. Breaking is always endo. Remember, forming is always exo. So, this is kind of a endothermic process. You need energy to do this. Breaking off an electron, okay? Now, what to note here is that if you're looking at this magnesium example, you see this is magnesium. It is easy to remove the first one, okay? The ionization energy is like 735, not too high. It's also easy to remove a second one, right? You have 1445, a little bit higher in amount, but still reasonable. What happens when you try to pull off a third from magnesium? It jumps up quite a huge amount. Why is that? Because core electrons are bound a whole lot more tightly than valence electrons. So if you're pulling off a core electron, your ionization energy dramatically increases. And that's going to differ from group to group. So like group 2, they'll let you pull off 2, but they don't want you to pull off a 3 because then, they're pulling off a core electron. Group 1, you can pull off 1, but you try to pull off a second. Group 1 are the alkali metals. They go to +1. They only want to pull off 1. You try to pull off the number 2, you're going to get a huge jump in your energy. Okay? So, group 13 or 3A, pulling off that 4th electron is where the jump in the energy goes. Okay? So keep that in mind. So in general, as we go across a period from left to right, the first ionization energy increases. And remember, first ionization energy is pulling off the first electron. Second ionization energy is pulling off the second, and so forth, okay? Electrons are added in the same principal quantum level and do not completely shield the increasing effective nuclear charge. You're adding more protons in faster than you're having electron repulsions, so that pull of the nucleus is going to hold on to that electron more tightly. So the energy needed to remove it is going to be higher. Okay? Electrons in the same principal quantum level or principal energy level are generally more strongly bound from left to right on the table. So you get over to your noble gases. Guess what happens with your ionization energy when you get to those noble gases? Super, super, super astronomically high, because guess what? Those noble gases are stable and they don't want to lose anything. Okay? So theirs are ridiculously high because they're stable. They don't want to lose electrons. All right? Makes sense? Okay? So let's talk about that effective nuclear charge is what's really causing the more holding on to the electron. As you add more protons, you have more attraction, more Coulomb attraction. So it's going to be holding on to it tighter. So that's why, say, fluorine is going to be a lot harder to remove an electron from than, say, lithium. Okay? Fluorine has 9 protons. Lithium only has 3. Definitely going to have more effective nuclear charge there. Okay? Now, does anybody remember the general trend for the groups, the columns? So, if you go, I like to think of them as going the same direction. So if I'm going left, I'm going up and to the right, I'm going to be increasing. So if you are going up a group, ionization energy is going to increase. If you go down the group, it will decrease. So depending on how you remember it from last year, okay? So in general, as we go down a group from top to bottom, the ionization energy decreases. But I like to think of it as going up and to the right, because therefore they're both going to increase. Up and to the right, both increase. Okay? Left and down, they decrease for this particular one. Basically, what's going on here, if you go down a group, the distance from the nucleus is a lot greater. You have more core electrons, so less effective nuclear charge holding on. So they're much easier to remove when you have bigger atoms. More core electrons, you can remove them without as much energy. Okay? So that's the gist of going down the group. Okay? So let's take a look here at our values of first ionization energies for the elements in the first 6 periods. If you look here, your next concept check is looking at, why is this not just a straight, nice line like that? What do you see there going on? There's a few little ones that dip and don't follow the trend exactly. Does everybody see that? So, we have to figure out, like, why is nitrogen's ionization energy slightly higher than oxygen's? If we're following the trend exactly, oxygen should be higher, right? We're going to talk about those exceptions here. Beryllium, It's slightly higher than boron. If we're following the trend, boron should be higher, but no, there's exceptions here. And why is that occurring? Why is it not linear? We have to look at the configurations and the orbital diagrams to tell, because it's really because of some electron repulsions going on. Okay? And I'm going to show you those exceptions in just a minute. But those electron repulsions between those two separate groups cause just a slight little deviation of our normal trend. Okay, and now I'm going to draw out the orbital diagrams to give you as an idea as to why. Okay, so let's look at those examples here. This is between 2A, which is your alkaline earth metals, and 3A, which is your boron group. Okay, so I'm going to draw them over here. So for instance, say on beryllium. I have 2S, it's completely filled, right? Like so. If I have boron, I have a 2S, right? It's filled, but what else do I have?
Oh, and you have only one part filled, so it's less stable.
So I have one in my 2p here, right? Okay. So taking one out of a completely filled energy level like that, okay, where it is, pretty stable there, okay, it's going to be a little bit more difficult to pull it out of here. This third electron in the boron causes more repulsions. So when you have more repulsions, it's easier to remove. Doesn't take as much energy, so that's where you get a slight little change in the energy there, because it's easier to remove the 2p1 because it has added in an extra little bit of electron repulsion than it is to remove it from the 2s for the beryllium. So you have, this one has a little bit more electron repulsions. And it's just a slight little difference, as you see. It's not like it's a huge amount of energy, but it just deviates slightly. Okay? So let's look at our other exception, which is between what? Nitrogen and oxygen. Okay? Which is group 4 and 5A. No, 5 and 6A. 5A and 6A. Okay? So, looking at nitrogen, 2p, right? 1, 2, 3, right? Oxygen, looks like so, correct? This is going to be 2p4. This one's going to be 2p3. In nitrogen, they all have their own separate orbital, correct? But in oxygen, one of the orbitals is filled. So this extra electron in here causes a little bit more repulsion. So guess what? This one's easier to remove. Just slightly, but that's why we get this little dip here. Okay? Just slightly easier to remove because of that little extra added electron repulsion. Yes?
So, in the case of fluorine, because there's one more, it would be easier to rather than.
No, fluorine continues to get higher because it gets more effective nuclear charge. So this electron repulsion, in comparison to effective nuclear charge, isn't enough to change the energy. So you have more repulsion here than the adding of the protons to counteract it. Fluorine, though, has more protons, so therefore it's holding on tighter. Does that make sense?
Yeah.
So you don't have that little deviation from the trend. Yes?
So the more repulsion like it has, the easier it is to take the electron.
It would, yes. But you remember that effective nuclear charge takes into account the repulsions and adding in the protons. Adding in more protons gives you more pull to keeping it more tightly bound. So it's kind of they're opposing forces. So as you add more protons, that's probably a little bit more of an effect than the electron repulsions, but this is where our two deviations take place. Okay? Concept check. Which atom will require more energy to remove an electron? And why? Which one? Chlorine is correct. But why? No, but when you're justifying it on the AP exam, you can't just say because it's further right in the period. What does it have more of? What's the key word you need to state in your justification? Has a higher effective nuclear charge. Because that basically is saying it has more protons to pull and hold it tighter. Okay, we're going for effective nuclear charge that's bigger for chlorine than it is for sodium. So yes, the effective nuclear, like in kinetics, they wanted you to say activation energy, right? Here they want you to say effective nuclear charge. Okay, more protons will cause, and in smaller atoms, the protons really play a huge role because there isn't a whole lot of electron repulsions going on. Okay, so like that's a big important one. All right, let's look at this one. Which atom will require more energy to remove an electron and why? Lithium or cesium? Cesium's down below in that same column. Lithium. Why? Higher effective nuclear charge because it doesn't have as many core electrons. So you don't have lots of shielding going on, right? It's a much smaller atom. So that effective nuclear charge is going to play a role. Good. Everybody get that? But remember, because when you have more core electrons, like cesium's in row 6, so it has principal energy level 6 all the way out there. It has lots of core electrons. So it has lots of shielding of that proton nucleus. Okay? Yes? Anything that's not a valence electron is a core electron. That's true. Yes, correct. All right. Which one has a higher second ionization energy? Second ionization energy. Why? Which one is it easier to remove electron to instead of?
Lithium.
So lithium has the larger second ionization.
Correct. Lithium has the higher second ionization energy because lithium has one valence electron, right?
Yeah.
So if you pull off 2, where are you pulling from?
Core electron.
You're pulling off a core electron, and remember we said core electrons are more tightly bound, they're much harder to remove.
Yes.
And it also creates an unstable atom, which they don't want to be unstable, so that energy is going to be higher. Okay? Make sense? No, for this case, yes, it's because of the core electron versus the valence electron. So this table shows you have this in your book, but I have seen this table inserted into like multiple choice questions. So as you can see here, this is like group 1A, this would be group 2A, and so forth, 3A, 4A, and so forth. So, as you can see the numbers, 1A only wants to lose 1, so when you get to that second removing it, you're removing a core, so that's where the jump goes from 495 to 4,560. So, if you're in group 2A, you're okay with removing up to here, but if you go to that third, that core electron, it's going to jump up a lot. Okay? All right, electronegativity, which we're going to talk about more in detail next time because we're going to talk about like dipole, and polar molecules. But ability to attract electrons when the atom is in a compound. And it increases right in the period. And the smaller the atom, the stronger the pull. So that effective nuclear charge comes into play. And it increases if you go up in the group. Once again, you're a smaller atom, more protons, less electron repulsion ratio there. So you're going to get a higher effective nuclear charge. Now your exception is going to be the noble gases because they do not have any electronegativity values. Why would they want to attract an electron when they're already stable? Does that make sense? That's right. They would, exactly. Okay? So keep that in mind when you're talking about electronegativity. Electron affinity. This is one we didn't really discuss a whole lot last year, so you do need to pay attention here. Okay? This is the energy change associated with adding an electron. Energy change with adding the electron. So adding an electron, this is a Coulomb attraction. Adding it to it releases energy, because remember, forming bonds is exo. Okay, forming is warming, it's exo, okay? In general, as we go across a period from left to right, your affinities are going to become more negative, because negative energies, remember, are exo. Positive energies would be endo, okay? And as you go down a group, you're becoming more positive. So the amount of energy released is going to be less. Okay? So more positive means just less energy is being released as you go down the group. Okay? So far, so good with affinity. Why what?
Why is more positive?
We're going to discuss that in just a moment. Yes. So, in general, electrons' affinity become more exothermic as you go left to right, and from bottom to top as well. Okay. In general, there are a few exceptions here too. The effective nuclear charge, of course, plays a role here too. And of course, being over in the right-hand side of the table, those are our non-metal anions, because they're seeking electrons anyways. They want to gain them. Like the halogens are at 7 valence electrons. They need to gain one to be stable. So they're looking to gain one. And if you have a smaller atom with the proton ratio to the electron repulsion, you have a higher effective nuclear charge. You're going to be able to attract it. Okay? And you're going to want to form that quickly, and you're going to be releasing a higher amount of energy, because that ability to attract it in and form that bond quickly releases more energy. Okay? Now talking about some of the exceptions. We're going to be looking at group 1 and group 2. 1A and 2A. Okay? As you see here, between lithium and beryllium, once again, the best bet is to look at the orbital diagrams here. So if I'm looking at lithium, I have 2s completely filled. No, lithium's not completely filled, is it? It's only one, right? So we have one electron in our 2s for lithium. But for beryllium, guess what? Our 2s is completely filled. Now, if we're going to gain an electron for lithium, you would gain it here. So this is where you would gain the electron. You would fill the 2s, right? That's good, whatever, it's going to release a lower amount of energy, but because really the metals don't want to gain electrons anyway, so they don't release a whole lot of energy. But if beryllium gains a third, where is it going to gain it? It's going to gain it over here, okay? Creating, more repulsions and stuff. So the tendency to want to do it is not very high, okay? Adding that one into the 2p and having to fill another energy level. Okay? So this is where that discrepancy is playing a role, because we're adding it into the 2p now. More electron repulsions there, and it's higher energy because the 2p is a higher energy level. So it's not as stable and wanting to do so. The next exception, as you can see hopefully up here, occurs between the carbon group and the nitrogen group. And it's kind of the same arrangement if you look at the orbital diagrams, look at where you're gaining them as to why there might be a slight discrepancy there. So if I'm looking at carbon, 2p, carbon has 2 looking at nitrogen, right? Carbon, nitrogen has 3 in there. So if carbon gains 1, where is it going to go? It's going to go there. If nitrogen gains 1, where is it going to go? Causing more repulsion. It's not, not as favorable. Okay, so the energy release, more energy release means more favorable, right? Exothermically decided is favorable for our thermodynamics and everything. More favorable to adding it to carbon than it would be to adding it to nitrogen, so that's where this other discrepancy that's quite large you'll see there, okay? So that's electron affinity, creating that repulsion, okay? So when looking at these exceptions, and you can memorize them fine, but I like to think of them conceptually and looking at their orbital diagrams. Oh, that's where the repulsion is going to occur, and that's why it's a slight little deviation, okay? Concept check. Now, I know it's written incorrectly on your paper, but this is what I meant to say. In each pair of the following elements, which has the most negative electron affinity? Most negative, remember, is the greatest amount being released, because remember we're talking about energy being released. So out of lithium and beryllium, which one's going to be the higher, more negative releasing? Lithium. We just talked about that exception. Very good. How about for fluorine or neon? Fluorine. Neon's really not going to want to gain, right? So not going to be having a huge effect there, because it's a noble gas. And carbon or nitrogen? Carbon. Remember, that's another exception. I kind of put the exceptions in here because these are the ones they like to ask in the multiple choice. They do it on ionization energy and electron affinity. Okay? All right. Atom size. Bonding radius. Okay? Half the distance between the covalently bonded nuclei. Okay? So that's what we're looking at here. It's not, they measure that and then they divide it by 2 basically, and there you go. There's your atomic radius. Okay? Now atomic radius, as we go from left to right, it's going to decrease because the effective nuclear charge increases. So those adding more protons pulls them in closer. Increasing as you go down a group, simply because you're gaining more quantum numbers. Quantum principal energy levels, and you're getting more shells, you're getting more core electrons, you're getting bigger due to that. And those core electrons are more repelling of each other, so that creates more space. So that's why atomic radius, would get bigger as you go down. Yes? So we're almost done here. But we're going to have to finish this one up, I think, next class. This just shows you a nice little picture of the sizes. Your book has sizes as well. So, if you'd like to start practicing Lewis dot, I gave you the sheet and I gave you the instructions to follow if you want to go back and remember from last year how to do so. But I do need the photoelectron spectroscopy by next class, so make sure you finish that. Uh-huh.